A matrix can represent a transformation. It moves and stretches vectors, but it does this in a consistent way across the whole plane. Here is our worked example. Let the matrix, call it A, have first row 2, 1, and second row 1, 2. First, let's apply this matrix to a simple vector, one component per line. Take the vector with first component 1 and second component 0. To find the new first component, multiply 2 by 1, then add 1 times 0, which gives 2. To find the new second component, multiply 1 by 1, then add 2 times 0, which gives 1. So the vector 1, 0 has moved to the vector 2, 1. Here is the two-dimensional view. The original vector points along the horizontal axis, and the new vector points diagonally, both longer and rotated. This shows the matrix moving the vector, not just stretching it. Now watch the same picture become three-dimensional. We add a height axis, so each vector sits flat in the plane, but we can now see the transformation as tilting a flat sheet in space. Next, let's find the eigenvalues of this matrix. In words, an eigenvalue is a number that tells us how much a special vector gets stretched without changing its direction. The formula is the determinant of the matrix A minus lambda times the identity matrix equals 0. Written out, that means the quantity 2 minus lambda times the quantity 2 minus lambda minus 1 times 1 equals 0. Expanding this out gives lambda squared minus 4 lambda plus 3 equals 0. Factorizing, this becomes the quantity lambda minus 1 times the quantity lambda minus 3 equals 0. So the two eigenvalues are lambda equals 1 and lambda equals 3. These are the two special stretch factors for this matrix. Now let's find the eigenvector for lambda equals 3, one step per line. Substitute lambda equals 3 into the matrix A minus lambda times the identity, giving first row negative 1, 1, and second row 1, negative 1. Multiplying this by a vector with components x and y, and setting the result to 0 gives negative 1 times x plus 1 times y equals 0. This simplifies to y equals x, so one eigenvector is the vector with components 1 and 1. Now let's find the eigenvector for lambda equals 1, one step per line. Substitute lambda equals 1 into the matrix A minus lambda times the identity, giving first row 1, 1, and second row 1, 1. Multiplying this by a vector with components x and y, and setting the result to 0, gives 1 times x plus 1 times y equals 0. This simplifies to y equals negative x, so the other eigenvector is the vector with components 1 and negative 1. Here is the two-dimensional view of both eigenvectors, shown as two lines crossing at the origin, one going up and to the right, the other going up and to the left. Now watch this same picture become three-dimensional, lifting each line into space so we can see the matrix acting like a stretch along two fixed directions. Check step, let's confirm the eigenvector for lambda equals 3 only changes in length, never direction. Apply matrix A to the vector 1, 1. The new first component is 2 times 1 plus 1 times 1, which equals 3, and the new second component is 1 times 1 plus 2 times 1, which also equals 3. So the vector 1 has become the vector 3, 3, which is exactly 3 times the original vector. The direction has not changed, only the length has, confirming that lambda equals 3 with eigenvector 1, 1 is correct.